Welcome back. Today we're going to be going through the full solution for an example where we need to find all the inflection points, determine the intervals where the function is concave up or down, and I've also applied the second derivative test to all the critical values. So let's dive in. Okay, so first, how do we find the points of inflection? So the points of inflection are points where the second derivative is equal to 0, and that causes the sign to actually change, right? The sign of whether the second derivative is negative or positive. So if it goes from positive to negative or negative to positive, then that means it is indeed a point of inflection. So in order to do this, I'm first just going to find the derivative. So what's the derivative? According to the power rule, derivative would be 4x cubed minus 12x. And then the second derivative would be the derivative of that derivative, which is 12x squared minus 12. Okay, and next I need to find all the points where x would be equal to 0. So, not where x would be equal to 0, where the second derivative would be equal to 0, because that indicates a potential change in concavity, a potential point of inflection. So we're going to set the second derivative to 0 and give 0 is equal to 12x squared minus 12. That means 0 is equal to 12 times x squared minus 1. That means 0 is equal to 12 times x minus 1, x plus 1, like that. Okay, so what does that tell us? Well, that tells us that when x is equal to 1 or negative 1, we have a point of inflection. Because notice that either of those points would be a change in the sign in that case, right? Now, if we had like a squared here or something like that, that wouldn't be the case, right? Because what comes out of a squared is always positive, but we don't in this scenario. That's just hypothetical. And so, therefore, these both would be points of inflection. So the points of inflection would be at x equals 1 and x equals negative 1. Now notice they didn't just ask for what are the x values of the points of inflection, they wanted the points of inflection. So I'm going to be plugging in 1 and negative 1 into my original function in order to get the y coordinates of both of these points. So that's commonly something people forget to do, so don't forget to do it. So f of 1 is equal to 1 to the power 4 minus 6 times 1 squared plus 5, which is equal to 0. And then f to the power, or f of negative 1, is negative 1 to the power 4 minus 6 times negative 1 squared plus 5. And I believe that is also going to be 0. Yes, that's also 0. Okay, so therefore, the points of inflection, I'm going to write this down, points of inflection are going to be 1, 0, and negative 1, 0 as well. So those are our points of inflection. Okay, part B says to determine the intervals where f is concave up or concave down. Okay, so the intervals are going to be with respect to x. So the thing is, we have a change in concavity at points of inflection at 1 and negative 1. Those are x values of those changes. So therefore, I need to test from negative infinity up to negative 1, then from negative 1 to 1, and then from 1 to infinity. These are the three intervals that I must test for, okay? So how do we do this test exactly, and what does it mean? Well, basically, we have to test everything before the first point of inflection, then everything between the 2 points of inflection of 1 and negative 1, and then everything after that second point of inflection. So that's how I came up with these intervals. And basically, in this case, any one point on the interval speaks for the entire interval. And so I'm going to be plugging in any value that I want between negative infinity to negative 1 and see if we get something positive or negative. Recall that when the second derivative is positive, it means that the original function is concave up, and if it's negative, then it's concave down. So let's plug in our values and see. So for the second derivative, I'm going to choose negative 2 because that is somewhere in the interval from negative infinity to negative 1. We're going to get 12 times negative 2 squared minus 12, which is 12 times 4, 48 minus 12, which is 36, and that is greater than 0. So therefore, we got a positive answer that's greater than 0, and that indicates that f is concave up. Then I'll plug in something between -1 and 1, which let's go with 0, that seems easiest. Always take that path of least resistance. So we'll get 12 times 0 squared minus 12, which is -12, which is less than 0. So therefore, we're going to put a minus sign here, and this is concave down. And then if we were to do something between 1 and infinity, say 2, for example, we would get 12 times 2 squared minus 12, which is 48 minus 12, which is 36. That's also greater than 0. It's positive, and so that indicates we're concave up. And so therefore, the concave up intervals are negative infinity to -1 and 1 to infinity. And then from -1 to 1, it's concave down. And then at the points -1 and 1, what does that mean? That means that those are the critical values, right? Those means that that means that those 2 points are the points where we switch from concave down to concave up, or vice versa, right? So those are kind of our, I don't want to say turning points because that makes it sound like, switching from increasing or decreasing, but kind of the equivalent of turning points, but in terms of the concavity, a concavity switch. All right, so part C says to apply the second derivative test to all critical points. So actually, so far we haven't even found all critical points. What we did is we found just the points of inflection, which are a version of critical points. But we also need to figure out, we need to use the second derivative to find minimums, maximums, all that kind of stuff. So all critical points. So part C is going to be somewhat separate here. So for C, first thing I'm going to do is I'm going to actually remind ourselves that this is our first derivative, and I'm going to set that to 0, and we're going to test all the critical points. So first, in order to test them, we actually have to use the first derivative to find all the critical points. So for part C, I'm going to start by setting our derivative equal to 0, our first derivative to 0. That means 0 is equal to 4x cubed minus 12x. And then what we can do is we can factor out 4x, so 4x times x squared minus 4, and then we can also factor x minus 2 times x plus 2 since we have our difference of squares pattern. So that means my critical values are x is 0, x is 2, and x is -2, or at least these are my critical x values here. Next, what I'm going to do is I'm going to use the second derivative test to determine if these are minimums or maximums. If the, actually I'm going to write this down, that if the second derivative is positive for a critical value, that means that we are concave up, and that means local min. If it's negative, that means local max. And it shouldn't be 0 exactly, because we already determined previously that the points of inflection where we had 0 exactly are -1 and 1. So we know we definitely will not get 0 exactly. So now let's put that to the test. As a reminder, the second derivative was 12x squared minus 12. So then we're going to put in 0. So if we put in 0, we get 12 times 0 squared minus 12, which is -12, which is less than 0. So that means local max at that point. Then if we do positive 2, we're going to get 12 times 2 squared minus 12, which is going to be, well, what's that going to be? That's going to be, well, we already figured it out actually earlier. That's going to still be 36, which is greater than 0, which means a local min. And then if we do -2, we also get a greater than 0, which means concave up, which means a local min. So therefore, there's a local max when x is 0 and a local min when x is 2 and x is -2. Now, you might be saying, oh, we already did these calculations. It's actually kind of a coincidence that in this case, these would be the same calculations as before. Before we were doing it because we wanted points that were in between the critical values, before the first one, after the second one, right? We wanted all those different ranges there. In this case, we're doing it because we actually want the to find out whether at these specific values that are minimums and maximums, if we're concave up or concave down. So we did kind of already do the same math earlier of 0, 2, and -2, but that won't always be the case. We might have found different values here in particular, and that would work too. Then the last step is it's asked us to test all the critical points. So I'm going to find where the critical points were. Recall that the original f of x function is x to the power 4 minus 6x squared plus 5. 6x squared, rather, plus 5. And so then I'm just going to plug in these values to find the other parts of our critical points. So f of 0 is 5. F of 2 is equal to 2 to the power 4 minus 6 times 2 squared plus 5, which is 16 plus 5 minus 24, which is -3. Yep, -3. And then we have that f of -2 would also be -3. So therefore, the critical points would be 0, 5 is a local max. And then 2, -3, and -2, -3 are both local mins. And so there we go. That's our final answer. Now, as always, if you do have any questions for any of that, feel free to leave those in the comment section, and we'll see you for the next one.